Over the past few decades, the use of glass in buildings has increased massively, not only as a glazing material, but also for construction purposes. Due to the application of glass as a structural element, and also due to the increasing size of glass elements being built, there is an increasing need for the development of relevant regulations. Although glass is nowadays a mandatory material in the construction of multi-story buildings, design rules for glass structures at the European level are only in the process of making. The purpose of any standard is to ensure a safe and rational design. The application of the standard in practice will cause a certain impact on the design economy. The aim of this video is to compare the economic effects of design according to the new Final Draft EN 19100, the current draft of Eurocode 10 for glass, to the standards that are already being used in practice. Please note that the technical quality, scientific validity, and the level of safety provided by each of the standards is not being taken in consideration, and some important parameters are disregarded, such as safety, robustness, impact resistance, post-fracture behavior, thermal, solar, acoustic, etc. The glass in the construction industry is used for many different applications with variable dimensions and compositions. For the purpose of the comparison, we have chosen the most common application: rectangular double-glazed insulating unit, either vertical as a facade element or horizontal as a skylight element, simply supported along all edges by a frame and loaded with a lateral surface pressure of 3-second gust wind load. Horizontal specimens experience also a long-term load due to the dead load of the glass acting in the same direction as the wind load. No other loads are considered. All verified units are composed of two monolithic panes. For the clarity of the procedure, laminated glass is not considered. The only comparison criterion is the minimal thickness of the glass required for the load-bearing resistance. The calculation is carried out on 3 different common glass compositions, and for each composition there are 3 different glass dimensions. In 2023, final draft for Eurocode 19100 was released. A comparison has been made with existing and widely used standards, American ASTM E1300 and EN 16612. Calculation according to the ASTM is expressed as a limiting value of the applicable lateral load, where load resistance is determined using 3 factors. These factors take in consideration glass dimensions, composition, and load sharing between 2 panes of the insulating glass. The glass resistance is compared to the characteristic load. On the other hand, calculation according to the EN 16612 gives us a design value of the bending strength for annealed and pre-stressed glass with its corresponding load factors. In the final draft EN 19100, design of the glass bending strength is based on the sum of the intrinsic glass strength and the surface pre-stress. Glass components are classified into 2 consequence classes. The results are shown in the form of graphs showing the capacity utilization factor as a function of the characteristic wind load. The capacity utilization factor, as the parameter used for assessment of the economy of the design, is the ratio between the design value of the effect of the actions and the glass resistance. For the capacity utilization higher than 1, the glass has not sufficient load resistance and the stronger glass has to be used. Curves are limited either by the capacity utilization factor 1 or by the wind load of 10 kilopascals. Since the limiting criterion according to the ASTM E1300 is the load resistance rather than the tensile stress, the capacity utilization takes the form of a straight line. The lower the curve, the lower is the utilization factor and the design is more economic. Results and their implications are pertinent to verified glass samples only, and although being indicative, they may not be extended to other geometry and loading without detailed analysis. For annealed glass, all 3 standards yield similar capacity utilization, and there is no clear economic advantage in the design of the analyzed annealed glass examples between the 3 standards. However, for the heat-strengthened and thermally toughened glass, final draft EN 19100 method provides lower capacity utilization than the other 2 standards. It may be concluded that for the analyzed examples, the design of heat-treated glass according to the final draft EN 19100 is the most economic, and the design using the ASTM 1300 is the least economic. This analysis clearly shows how the economy of glass design depends on the region and the respective governing standards. In order to maintain competitiveness in the market, researchers and innovations are necessary, and these types of analysis are the first step to it. In conclusion, while this preliminary analysis provides valuable insight into the economic implications of glass design based on the three standards, it is only a starting point. To gain a deeper understanding, further comparative analysis is needed, taking into account the parameters we have omitted in this study, such as safety, robustness, and long-term performance under various environmental conditions. A more thorough examination of these factors will help us better appreciate the full impact of different regulatory approaches on glass design. By extending the analysis to include these additional considerations, we can make more informed decisions about which standard best serves the needs of different markets and applications, ensuring not only cost efficiency, but also optimal safety and performance. This ongoing dialogue between regulatory bodies and the industry will continue to shape the future of glass in construction, helping us build safer and more sustainable structures.